My name is Chaitanya, physics faculty at Shakthi International School. Today, in this video, we are going to learn about Bernoulli's theorem. This is an important topic of class 11th chapter Mechanical Properties of Fluid. So, mechanical properties of fluids. Okay, we are going to discuss about Bernoulli's theorem. See, according to Bernoulli's theorem, what he explains in this theorem is this is about an ideal fluid. Now that ideal fluid should have some characteristics, that is, it should be incompressible, it should be non-viscous. Yeah, these are some characteristics of ideal fluid, irrotational as well. Okay, so now this is a part of hydrodynamics. Hydrodynamics. We are analyzing the fluid which is in motion, which is in motion. So if the fluid is moving in a pipe, okay, the Bernoulli's theorem explains if it is an ideal fluid, then the sum of, okay, the sum of pressure energy kinetic energy and potential energy of a flowing ideal fluid will always be constant. Okay, so if we are trying to prove this, the equation is written in this form: pressure energy plus half rho v square kinetic energy plus rho gh will always be constant. Okay, so now here I have to give one important detail here. Okay, that is, we are not talking about pressure energy alone or kinetic energy alone or potential energy alone. These are analyzed with respect to, always remember, with respect to volume. Okay, that means pressure energy per unit volume, kinetic energy per unit volume, potential energy per unit volume of a flowing fluid will always remain constant. That is the reason why instead of writing mass, I am writing here density. I hope you are understanding this equation. Now let us solve this equation and let us try to understand how we can get that equation. Let's say there is one pipe of this sort. Now let's say it is filled with a fluid. We are taking a cross section of fluid from the region here to here. Okay, now from here, if you are writing the parameters, you will have a pressure P1, the area of cross section is A1, the velocity that the fluid move here, the speed that the fluid move here is in V1. In the same way, here you can see the pressure will be applied in the opposite direction P2. This liquid is moving in this direction with the velocity V2. You are having an area of cross section A2 at this point. Let's say the liquid which is actually present in between these two markings is displacing a little to a new position. That means it has shifted from its initial position from here to here. So the change in it, let's say I'm taking it as, let's say it is initially x1 and it is x2. It has moved delta x, which is x2 minus x1. So this is the change in its position. Now whenever an object is changing its position, okay, These two liquids are at different levels. From the ground, if we are analyzing, this liquid is at a height h1 and this liquid level is at a height h2. Now, if you want to understand, if the liquid has to be moving, there should be some work that should be happening. Now, what is that work is, from where do you think that work is being done on? It is due to the pressure the work is being done. In general, the formula of work is force into displacement. Now, if you want to understand the force that has moved this, we can understand the force due to pressure. We know that we know that force F1 can be written as pressure P1 into area A1. Force F2 can be written as pressure P2 into area A2. The net force on this entire equation, F net, can be written as F1 minus F2. Why F1 minus F2? Because F1 is greater than F2. That's when the liquid is actually moving. So you can write this equation as P1A1 minus P2A2, and the displacement here we are having it as delta x. If that is a condition, then you can write your work done equation as P1 into A1 into delta x minus P2 into A2 into delta x. So now, if the change in volume is constant, then you can write P1 into delta V minus P2 into delta V, because A2 and delta x is the change in volume, A1 and delta x is also the change in volume. So you can write that work done as P1 minus P2 into change in volume. So this is a formula for work done. Work done due to the pressure of that fluid. Now this work will be utilized in two different ways. One, this work is utilized to change the kinetic energy, and this work is utilized to change the potential energy. So we can write work done is equal to change in kinetic energy plus change in potential energy, because any work which we are doing will be changing the internal energy of the system. So this work will be utilized in this. Initially the kinetic energy of that is half mv1 square. The final kinetic energy of it can be written as half mv2 square. Now initial potential energy of it, if you want to find the change in potential energy, initial potential energy of it is at mgh1, final potential of it is at mgh2, where m is the mass of the object, that mass of the liquid that is being displaced. So if you want to write change in kinetic energy, you can write it as half m into v2 square minus v1 square. In the same way, change in potential energy can be written as mg h2 minus h1. So since, according to the conservation of energy and work energy theorem, we know that work done is equal to change in kinetic energy plus change in potential energy. So if you are substituting, that is P1 minus P2 into change in volume will be equal to half m into V2 square minus V1 square plus mg into H2 minus H1. Now further, if we are taking that pressure P2 minus P1 as P, some general pressure, is equal to, so P1 minus P2 into, we are cross multiplying the delta V downwards, half mass by delta V, change in volume, into V2 square minus V1 square plus m by delta V into G into H2 minus H1. So now mass per unit volume, you know mass is volume into density. So mass per unit volume, change in unit volume will be written as density of that particular mass. This mass m, when I am writing here, this is the change in the position, the mass which has been changed. You can write, in fact you can write it as delta m as well. So no need to bother about that one. You can write m by v as rho. So rho into v2 square minus half rho into v1 square. Since the density is going to be constant, I'm not changing the density, because the objects, the ideal fluid characteristics is that it is incompressible. If it is incompressible, the density is not changing. In the same way, rho g h2 minus rho g h1. You can write this one as P1 minus P2. Now if you are redistributing this, you can write P1, I am sending all the initial parameters one side, rho 1 square plus rho g h1 is equal to half. You can write this one as P2 when it is moving from here. You can write it as P2 plus half rho V2 square minus, sorry, plus rho g h2. So this is the general formula. Okay, this is what concludes that pressure energy per unit volume and kinetic energy per unit volume and potential energy per unit volume, potential energy per, I will write it again here, yeah, potential energy per unit volume will always be the sum of potential energy, kinetic energy and potential energy per unit volume will always be constant. Okay, so I hope you understood this Bernoulli's theorem and the principle behind it. Okay, we'll meet in the next video. Thank you.